Hey everyone, Katrina here, and today we're going to talk about the end behavior of polynomials. Be sure to subscribe for more videos like these. Okay, so I previously talked about polynomials. I've given us some information about what they are, how we can spot them, and some really neat properties. So be sure to check out those videos as well. Today we're going to talk about the end behavior of polynomials. This is a really important discussion that kind of motivates a lot of calculus, limits, and continuity. But we're not going to worry about calculus yet. We're just going to look at our polynomials and determine the end behavior of them. So first of all, what is end behavior? Essentially, end behavior is what happens to a function as we approach plus or minus infinity. So let's just take a second and appreciate what infinity means here. So infinity is not a number. So it's actually a concept. So in mathematics, especially when you get higher up in calculus, we often talk about this concept of infinity. Infinity is an infinitely large number. It's a number bigger than any other number. So you can never actually get there. You're always trying and trying and trying to get to infinity, but you'll never arrive. Same with negative infinity. So that's why it can never be classified as a solid number, but this concept of getting increasingly larger and larger. So that's what we're going to look at today. We're trying to determine what happens to our function as we approach this mysterious concept of infinity. So I'm going to show you the hard definition, but before we get into that, let's go through a motivating example together so that we're all on the same page. So when we deal with infinity, this is one way how we can write it. We're essentially asking ourselves, as x approaches infinity, what is y approaching? That's kind of the main concept of end behavior. So looking here, we have our x and y axis, and we're looking, so when we go towards the right, so this, what I'm drawing in the green arrow here, is x approaching positive infinity. So as we travel along the x-axis all the way to infinity, what's happening to our y function? We can see based off of this arrow that as x is going to infinity, we see that this motion is going to continuously go upwards. So that means that we are going towards positive infinity in our y-axis. So we can write that here. So as x goes to, you can write infinity or you can specify positive infinity. As x goes there, y is also going to positive infinity. Okay, but what about the reverse? So what happens, so we'll just give us, sorry about that, give ourselves some more space here. So as x approaches negative infinity, what's happening to y? What is y approaching? So as we travel down the x-axis in the negative direction over here, so we're approaching, x is approaching negative infinity, what's happening to y? So you can see that our curve is continuing to go down, is continuing in the downward direction. So that means it is continuing towards negative infinity. Therefore, as x approaches negative infinity, y is also approaching negative infinity. So this over here is one method that you can use to write out your end behavior with your infinity notation. Another method I'm going to show you right here is called the quadrant method. So we can write out, if we have our Cartesian plane, so our xy axis, we can write our quadrants in the following way. So the top right one is quadrant 1, top left is quadrant 2, bottom left is quadrant 3, and bottom right is quadrant 4. So if we look at this exact same example here, how can we solve it using our second method over here, which is our quadrant method? Well, what you want to do is you want to figure out where does it start, kind of quote-unquote start, versus where is your function ending. And you're always going to go from left to right when you do this type of analysis. So on the left side of our graph, let's see where a function exists. We can see that it exists right over here. So that means that it's going to be starting then, let's write this in a different color. It's starting in our Q3, and then where is it ending? Well, we can see that it's going to be ending around here as it continues to go upward, that it is going to end then in quadrant number 1. So we can also write our end behavior that it goes from Q3 to Q1. So one of the most important things about end behavior is that we don't care about local behavior. What that means is all this stuff like happening in the meantime in our countably like discrete values over here in the middle, we don't really care. We don't care if y goes up to infinity and back down in the meantime, or if it swirls around. All we care about is what happens to our function as x either gets really large, so as it approaches infinity, or really small as it approaches negative infinity. So that's why with our quadrant method, we just care about kind of what's happening right at the beginning, as close as we can to when it starts, to right at the end. So these functions in themselves are infinite. That's why I put the quotes around start and end, because they have no real start or end date, but it's kind of that behavior. So as it approaches the start, so as it approaches negative infinity, all the way, and then we care about what happens as it approaches positive infinity. So we don't care about that in-term behavior. We're just looking at the end. Okay, so we were able to solve this by looking at the graph over here as a good motivating example. But now I'm going to show you a very concrete way how you can determine the end behavior of polynomials. So here I'm going to show you two key pieces of information that tell us a lot about how a polynomial function behaves. So the first thing we're going to look at today is the sign of the leading coefficient. And when I say sign, I'm saying is the leading coefficient positive or is the leading coefficient negative? And if you recall from my previous video, the leading coefficient is a coefficient that is multiplied to the term of x that has the highest power. That's a bit of a mouthful. So basically whatever the highest power of x is, and the coefficient that's stuck to that term, that's your leading coefficient. And if you correctly write your polynomial in decreasing order of power, then your leading coefficient should be the first coefficient that you have from left to right. Okay, now that we've said all that, let me show you what this means. So if you have a positive leading coefficient, then you're going to end in Q1. Okay, so that means that as ending in Q1 means that as x approaches positive infinity, y is also approaching positive infinity. Okay, so if you have a negative leading coefficient, what's going to happen? It's going to end in Q4. So what is that telling us? That's telling us that as x approaches, what would we have there? End in Q4. Q4 is over here. So that means that as x approaches positive infinity, our y is going to approach negative infinity. So it's going to be opposite. So that is already a great piece of information for us. The second thing that we can figure out is we can use the degree of the polynomial to help us determine kind of where it would start. So here, the sign kind of tells us where it ends. So we know that second half. But what about where it starts? So this is where we have to break it down into even degree and odd degree polynomials. So the degree of the polynomial corresponds to the degree of the highest power of x. So if we have a odd polynomial, then the starting quadrant is on the opposite side of the ending quadrant. Okay, so if you think about our typical y equals x to the power of 3, we see that this is odd because it has an odd degree, and we can see that it starts over here in Q3 and it ends in Q1. So it starts on the opposite side of the x-axis. We have our x-axis here, and it's going to cross the x-axis. Odd degree polynomials will always cross the x-axis. So that kind of helps us understand the, this behavior of end behavior a little bit more. Even polynomials will start and end on the same side of the x-axis. So if we were to look at this one, for example, we have y equals to x squared. We can see that it stays on that same side of the x-axis, starts and ends the same side. We can even have another one. Let's do something like this. Call it y equals x to the 4 plus whatever other terms, but we know that it's degree 4. And in this case, we can see that it does start and end on the same side of the x-axis. So that gives us more insight on the end behavior of the polynomial. So if we were to combine this, for example, with 1 and 2, in this case, sorry, this one should be negative here because it's facing downwards. So if we look at, we'll just call this EX1, example number 1, we can see that our sign of the leading coefficient is positive, so our LC is positive, meaning that it's going to end in Q1. So end in Q1, which is what we see here. And then also, since it is even, we know that it's going to start and end on the same side of the x-axis. So if it ends in Q1, that means that it has to start in Q2. For EX2, our example number 2, what do we see here? We see that our leading coefficient is negative. So if it's negative, that means it's going to end in Q4. So we can write that. So end in Q4, which is exactly what we see over here. And also it is a even. So that means that it's going to be on the same side of the x-axis, meaning that it has to start in Q3. And lastly, let's look at this guy over here. We'll call this EX3. We see that it is positive leading coefficient. So it's going to, positive leading coefficient means end in Q1. And we also see that it is an odd function. So that means that it's going to start in the opposite side of the x-axis, meaning here that it has to start in Q3. Okay, so we did a pretty comprehensive deep dive on end behavior, and now you know how to look for it graphically, but you also know these two really great rules over here, how you can look for the sign of the leading coefficient and the degree of the polynomial to determine what is the end behavior. So where does it start and where does it end? What happens as x approaches positive and negative infinity? And with that, I really hope you subscribe to more videos. We'll be talking lots more about polynomials and many other things. So I look forward to seeing you again, and comment any questions that you have. I'll get back to you soon. Goodbye for now.